Hello everybody, this is Professor Iris Miano giving you your, let's see, I know it's week 6 and day 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, week 6 day 11, if I'm not mistaken. Excuse me. Lecture video, and it's just one section long, so it'll be relatively short. It's on convex polygons. So most recently, we had a pretty thorough discussion about triangles, and we'll continue to talk about triangles in this section, but also expand the discussion to, higher order polygons, 4, 5, 6, 7, 8, all the way up to 10-sided polygons, as far as like what names you're expected to know. And we'll get crazy with the topic and go a little outside of our curriculum just for fun for a moment. I hope it's not seen as anything too terrifying. I just think it's a little fun to learn how to name some polygons that have like literally hundreds of sides. We'll get to that in a second. And then we'll have, I want to say at least a corollary or two about some of the relationships between interior, exterior angles and the like, and then we'll wrap up our discussion with a couple of notions about polygrams, which are some non-convex. We'll get to that in a second. Sorry, I'm trying to get real super detailed with my introduction here, but let's just go ahead and dive right in and define what a polygon is to begin with. It's a closed plane figure whose sides are line segments that intersect only at endpoints. So I have some space provided for you on your lecture notes where I want you to come up with an example of a polygon, something that looks like a polygon that follows the definition, and something that's not a polygon. So I'll give you some guidance here right away as to what would be good examples. You can come up with other ones, certainly, but a polygon must have straight line segments. It doesn't say straight here, but they can't be curved, okay, in order to be categorized as a polygon. So here what we have is just a rotated square, it looks like. One might say, oh, that's a diamond, right, because it's just, tilted from its normal square position, but it looks like it fits the definition of a square because I'm assuming that all of the edges are the same length and that all of the interior angles are right angles. While that's not the formal definition of a square, we'll actually get into what the formal definition of a square is. It's a little bit less information than you might think it is, which I think is kind of fun. But anyway, if we're talking about a quintessential diamond shape, that's actually technically referred to as a rhombus. We'll define that a little bit later as well in the semester. Okay, but I want to highlight why this figure over here is emphatically not a polygon. It violates the definition a couple of different ways. Some of these trajectories are curved. Well, in fact, all of them are curved. And it looks like we have endpoints for the trajectories that are inside the figure, not connected to any other trajectory, right? Or line segment. There's no line segments in it, in fact. So for that, even though it is technically closed, right, there's no open end, there's no way you could using your pencil kind of enter into the figure without crossing an edge. That's what would be mean by an open plane figure, but yeah. So hopefully it's very clear how this cloud-like drawing here is not a polygon. Cool. Now, among the polygons, there are two different types. You can either be convex or you can be concave. Or and when I was in your position learning these particular concepts regarding polygons, we called them convex and non-convex. So the fact that this textbook and the curriculum here at SMC calls it concave, I'm just like, it's weird to me. I used to call it non-convex, but concave is a little bit, I don't know. Feels less robotic as a describer rather than just the thing. Anyway, what are the definitions for these terms? Convex polygons are polygons whose interior angles all measure less than 180 degrees, okay, whereas a concave, the alternative would be a polygon that has at least one reflex angle. Do we remember what a reflex angle is? It's some angle that measures larger than 180 degrees. Okay, so I'll have a couple of examples that you can copy down onto your lecture notes like so. Okay, so here we have what appears to be a nearly regular, I'll define what that term means. That term actually means something particular in this context. Polygon that has, let's see, let's count them off. Here's 1, 2, 3, 4, 5, 6, 7 edges. 7-edged polygon. That is what we will learn very shortly, called a heptagon. Okay, so this looks like it's convex because there's no exterior angle that you could measure that's or sorry, interior. Sorry, I meant to say interior. There's no interior angle that's greater than 180 degrees, right? 180 degree angle would be a straight angle, so we definitely are clicked in from a straight angle situation in regard to all of the interior angles. Whereas this plus sign looking polygon, which has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges. So what's the term for a 12-edged polygon? It's actually a dodecagon. Not that you need to know that, but it's just kind of fun bit of trivia. Notice that this and other interior angles measure something more than 180 degrees. So that's a reflex angle right here. In fact, I believe this angle, if we're assuming that this angle on the exterior here is a 90 degree angle, then this interior angle would be 270 degrees, definitely bigger than 180. And so therefore a reflex angle. Another way you can determine if your polygon is concave is to do the connect the dots test, which is to say, if you were to put 2 dots in the interior of your polygon such that the straight line connecting them travels outside of the polygon, then the polygon is concave. Okay, so they don't talk about this dot test in the textbook, but that's something that I learned when I was in geometry class, and I thought I would share that as well. Okay, but sticking to the definition is always a good idea. All right, here's where we get into naming polygons, and here is the exhaustive list of polygon names that you are meant to internalize, okay? So notice that there's no two-sided polygon, because if you just have 2 edges met by a vertex, that's just an angle, and it's an open situation. It's not closed. It can't close unless there's some kind of curved edge, which would violate the definition of a polygon. So the minimum number of edges that a polygon can have is 3. And we know that 3-edged polygons are called triangles. 4-edged polygons are called quadrilaterals, okay? And we have to have this kind of generic terminology for this because there's lots of different types of 4-sided figures that we can talk about. We have an entire section coming up, I want to say in chapter 5 or 6. Nope, chapter 6 is when we get into 4-sided business. Yeah, so chapter 6 we get into all the quadrilaterals that we care about in this curriculum. They include parallelograms, squares, rectangles, rhombi, which is the plural for rhombus, so on and so forth. Okay, 5-sided figure is called a pentagon, and then the names for the different polygons get into more, I mean, they're all Latin-based, but they're very systematic in their naming. It's basically something agon, something agon, something agon, all the way down, right? So penta means 5, if you break it down to its like Latin roots, and then gon just means sides, I guess, 5 sides. Hexagon has 6 sides, a heptagon has 7 sides, octagon, 8 sides. We know this one is terribly famous for various reasons. Probably the most basic example is a stop sign, right? Nonagons have 9 sides, decagons have 10 sides. Deca is probably a really easy root word to come across for a lot of folks. Just, I don't know, I feel like it comes up more than nona, right? Who's even really heard of nonagons happening in real life. Oh, another thing that I want to mention is that hexagons are super indicative of, you know, a natural kind of a, what's the word, maximized lattice space. So, like bees make their honeycombs using hexagonal shapes for their little cubbies that they put their larvae in, and that would eventually are filled with honey. So, you know, these some of these happen in nature, but not, anyway. I'm rambling here. Here's the other thing that I wanted to call to your attention is that it can get wild with trying to name polygons that are having a lot of sides to them. So what some folks in the math department at Kutztown University, I don't know where that is, but they nerded out super hard on coming up with a scheme for naming polygons with, a lots of sides. So you can, for more than 20 sides, construct the name by using so-called combining prefixes. So here's the list, right, of all of the prefixes you would need in order to name something from 3 to 99 sides. And so they have an example for you here. If you needed to name, for whatever reason, a 35-sided polygon, it's called a triaconta chi pentagon, and the breakdown is kind of parsed up like so. Okay, if you needed to name a polygon with just shy of 1,000 sides, 100 to almost 1,000, then you can use this hecta prefix in order to, what is it? Hexahecta, or sorry, hexa would be the 6 for this little example that we have here. Hecta means, 100, basically, right? Hexa means 6, hecta means 100. So if you're trying to name a 672-sided polygon, you would break it up in this way. It'd be called a hexahecta heptaconta chi digon. So fun, right? And they give you little challenge ones. We'll just do this 83 sides together. So remember, 83 sides. Let's go back up here. So if you're 30, you want to look here to the tens digit. That would be octaconta. And if it's 3, the other prefix would be tri. So I believe that 83 sides would be a octaconta chi trigon. Let's see. Yep, look, 83 equals octaconta chi trigon. LOL. All right, so just a little bit of fun there. Please just ignore that. If you were like, no, let's just stick to the curriculum here, by all means, let's do so. Let's get back to work. Inside of a polygon, you could connect some vertices that are non-adjacent to each other, or not consecutive, I guess, is if you're going to take formally from the definition here, and that is the same as drawing a diagonal. So enter into the discussion pentagon ABCDE. Okay, so I'm naming this pentagon by virtue of going around the figure in a clockwise fashion to list the vertices in alphabetical order. Another way to correctly name this pentagon would be pentagon AEDCB. As long as you go around the figure without going inside and making a diagonal, you're cool with the naming. And you could start at any vertex. Like for instance, you could also name this pentagon CDEAB. Okay, so anyway, you know the rules for naming. What would it look like to draw all the diagonals from vertex A? Well, you only have 2 of them here because the only 2 non-consecutive vertices in relation to vertex A would be D and C. So these red lines are the only 2 diagonals you can draw from vertex A. Now, what if you wanted to draw all possible diagonals from all other vertices? Well, then you would have this going on right here. And look at this figure inside. It's actually something that we're going to get to at the end of this section. It's a polygram. And since it's got a 5-sided figure inside of it, it's called a pentagram. Okay. So anyway, we'll talk about pentagrams again towards the end and other such polygrams. Now, what if you had a figure who had a lot of sides, maybe like a lot more than 5, and you wanted to know how many diagonals were possible to draw without actually having to draw them? Well, that's where theorem 4.5.1, this is the first theorem in section 4.5, comes into play. It has a relationship, an equation that helps you calculate the number of diagonals, D, which is based on the number of sides that the polygon has, N. So just plug in the number of sides that you have here and there and simplify the equation. So now for practice, let's entertain this exercise. How many diagonals does a 12-sided figure have? And I put parenthetically the name of a 12-sided figure, which I believe I alluded to earlier. It's a dodecagon. So let's go ahead and reference the formula from theorem 4.5.1, not that we want to remember it that way. It's the theorem that allows you to calculate the number of diagonals for any n-sided polygon, and plug in 12 for n, simplify, simplify, simplify. You got 54 diagonals. Whew. And so if this is information that you needed to have, aren't you glad that you just calculated it to figure out this incredibly high number of diagonals rather than having to draw them and count as you go, or worse yet, count after you drew them all down? Whew. What a painfully tedious endeavor that would be. So anyway, moving on. Just as a heads up, this doesn't come up a lot. It's just more or less kind of fluff information, but the rest of the stuff in the form of all the rest of the theorems are just, head and shoulders more relevant to stuff that we actually do and care about and could be tested on, just so that you're aware. The sum of the interior angles of a polygon will depend on the number of sides it has, which has been already generically deduced by, or represented by the lowercase n. So here's the next theorem, the second theorem in section 4.5. The sum, which we'll call capital S, of the measures of the interior angles of a polygon with n sides is this formula. And you only need to know how many sides the polygon has. You subtract it by 2, and you multiply it by 180 degrees. Okay, so it's an interior angle sum, so that means that the units associated with this S value that we're going to calculate should have degrees onto it. It's very important to me that when there is a units context in anything that we calculate, that our final answer captures that unit. So let's entertain a specific example and determine what is the sum of the interior angles of a 20-sided figure, which, if you're wondering what the name of a 20-sided figure is, it's an icosagon. Isn't that a cool name? Super cool. So let's go ahead and reference the appropriate formula, plug in n as 20, and then simplify, it's 3,240 degrees total. Now that's the sum of all the interior angles. If we happen to know that all of the interior angles are the same measure, we could divide by the number of angles in order to determine individual angle measures. But we have to know that all of the interior angles are the same. And there's a term for that, and it's called regular. If a polygon is regular, then it's equilateral and equiangular. So as far as using some of these formulas are concerned, knowing that they're equiangular by virtue of using this term, the way it's defined, we know that we could just simply take the interior angle sum and divide it by the number of sides to get a single angles measure. But it has to be regular in order to use this next formula that's going to be presented after we talk about the regular forms of each of the 3 through 10-sided polygons. Okay, so what you see here in your lecture notes and on the screen is an example of an equiangular and equilateral version of the 3 through 10-sided polygon. So this is a regular triangle, or an equilateral triangle is what it's more commonly called. An equilateral quadrilateral is called a square. We'll get into the formal definition of that in chapter 6. Here is a regular pentagon. Here's a regular hexagon, a regular heptagon, a regular octagon, a regular nonagon, a regular decagon. So again, these terms are not only designated to these perfectly formed regular versions. They just have to have the number of sides as indicated by their name. So what you're seeing right now on the screen is the regular versions of each of these types of polygons. Okay? Great, moving on. So if we have some such polygon, a regular one, and we want to know what the interior angle measure of one single or each interior angle we'll take that S formula and divide it by n. So here's the S formula. It's n minus 2 times 180 degrees. But if we just divide it by n, then we have the I formula. Okay? So when you get to know the I formula, you're kind of getting a 2-for-1 thing, where it's like if you just don't divide by the number of sides, you're getting the sum of all of the interior angle measures. So let's use this in our next example. It asks, what is the measure of one interior angle of a 15-sided polygon? Oh, and there's a word missing here. I'm so sorry. I meant to say of a regular 15-sided polygon. And I forgot this in a previous semester and forgot to update it. Okay, so just so you're listening, the way that this example should read is, what is the measure of one interior angle of a regular? Maybe just in your notes, go ahead and put like a little caret right there and write the word regular. That's supposed to be there. 15-sided polygon, which for fun is called a pentadecagon. So cute. All right, so we're going to reference the appropriate formula. We're going to plug in what for n this time? 15, because that's the number of sides that was presented in the preamble here. 15 is plugged in. Simplify, 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 and it looks like each interior angle of a regular 15-sided polygon, aka a regular pentadecagon, is going to be 156 degrees exactly. Okay, cool. I believe we are ready to talk about the sum of some exterior angles of a polygon, and it turns out that no matter the polygon, weirdly enough, the sum of all the exterior angles is always 360 degrees. That works for a triangle. It works for a hexagon, as pictured here. It works for an icosagon, which is a 20-sided figure. It works for a, what was it, octa, conta, chi, trigon, an 83-sided figure as well. It's just, it doesn't matter what the polygon is, as long as it is a polygon. We can take the exterior angles, which come about from extending line segments in such a way that you explicitly show an exterior angle, like you see in this 1 prime, 2 prime, 3 prime, 4 prime, 5 prime, 6 prime. And by prime, I mean these little like apostrophes. In mathematical shorthand, that's usually denoted by the term prime, which is like some sort of related item to its, you know, non-primed counterpart that's first initialized. So we have interior angles 1, 2, 3, 4, 5, and 6, and their exterior counterparts 1 prime, 2 prime, 3 prime, 4 prime, 5 prime, and 6 prime, just to be clear. So if you added up the measurements of all those exterior angles, it would be 360 degrees. And that would be the same if you had added up all of, 9 of the exterior angles for any nonagon. It's also going to sum to 360 degrees. So if you're interested on how this can be, I invite you to read the proof on page 219. However, it's not necessary that you do so, and it's not something you're going to be tested on, just so we're clear. The proof, that is, okay? You could be tested on something relating to this corollary, just to be clear. All right, great. Moving on. The last thing I wanted to discuss here are polygrams, which are specially defined concave polygons, and they always have this interior polygon structure because they are formed when you kind of attach isosceles triangles to the outer edges of a regular polygon, so to speak. So this dashed line here is like, you can assume it's a regular pentagon, and so the isosceles triangles kind of tacked on either all of the dashed edges is what form the pentagram, okay, which is a type of polygram. So, and you have to have 5 or more sides extended. So there are only polygrams for pentagrams, hexagrams, and upwards. Like you wouldn't have a polygram for like a square or a rectangle or anything like that. Well, it wouldn't be for a rectangle because I believe the interior polygon has to be regular. Anyway, there wouldn't be one for a square, according to the definition. Okay. Some things that we definitely want to note before we move on with any example, which we have one that we're going to tackle before we go. All sides of the inner pentagon, which is the dashed lines, have congruent isosceles triangles attached to them. Okay, so here's this guy right here that I'm outlining with my cursor. That's an isosceles triangle. So what does that mean? That means that this dashed line is the base edge and that these two edges are congruent to each other, all right? So we're going to keep that in mind. We're also going to keep in mind the base angles are congruent to each other. I'm giving you a lot of hints that are going to help us through this next example. So taking this particular example pentagram, and we're assuming that the inner pentagon is regular, what is the measure of angle 1 going to be? And believe it or not, just knowing that the inner pentagon is regular is enough information for us to find the measure of this particular angle right here. I kid you not. Now watch. Here are the series of steps that we'll want to take in order to eventually get the measure of angle 1. So we're going to have to create some other angles and find their measures along the way. So let's go ahead and pick an interior angle in the dashed pentagon in order to find its interior angle measure. So let's entertain angle 2. You could have easily put your angle 2 over here, but you want it to be touching this isosceles triangle that contains the angle that you're trying to find the measure of. So what would be the measure of angle 2 here? Well, it would be the I formula, right, value. You would use the I formula in order to calculate it, in which the n value would be a 5. So for this regular pentagon, you take the number of edges minus 2, multiply by the 180 degrees, and then divide by the number of edges. And in simplifying all that down, you will find that the measure of angle 2 is 108 degrees. Cool. Now, go ahead and find the base angle of the isosceles triangle by noting that angles 2 and now just recently introduced angle 3 are what? They're supplementary to each other. They form a straight angle. So that means the measures must sum to 180 degrees. So take 180 degrees, subtract off the measure of angle 2, which is 108 degrees, and you're going to get the measure of angle 3, which is 72 degrees. Cool. Now, we know something about the interior angle sum of a triangle from the previous section, but what do we know about this angle's measurement? It'd be nice if we knew, at least 2 out of the 3, so then we could, subtract our way into finding the measure of angle 1. But what is the measure of this guy? Well, remember, this triangle on top, which contains the angle we're trying to find the measure for, it's isosceles. And isosceles triangles have congruent base angles. So whatever the measure is here, which we just calculated, 72 degrees, the measure of angle 4 also has to be 72 degrees, okay? Because base angles for an isosceles triangle are congruent and therefore have the same measure. All right, so we have two 72-degree angles. We can add them up and subtract it from 180 degrees, which we know has to be the interior angle sum of any triangle, and that's going to allow us to get the measure of angle 1, which is 36 degrees. And that's it. That's our final answer there. We did it, and we had just an incredibly minimal amount of information in order to get there, but we used a new formula that was presented in this section. Great. Let me know if you have any questions about that in class. Here's a fun fact that I want to leave you with before I remind you about the homework in this section. A polygram made from a heptagon called a heptagram has a fun, common name, and it's called an elven star or a fairy star. So if you're into that fantasy genre stuff, it's just, I don't know, so super cute. And people can get real fancy with their representations of it, as you can see here in this beautiful red and yellow and blue situation. They can get real crazy. And also a heptagram was featured in Game of Thrones as the the 7-pointed star, which was like the religious representation given to the religion that was discussed in Game of Thrones. So if you followed Game of Thrones, you've definitely seen a heptagram, like anytime they were in some kind of sept or a religious house. That's it for today. So please try these problems out. Let me know if you have any questions about this lecture or the homework when we meet again in class. Take it easy, guys. See you soon.